In the last class we have seen that if you have a periodic orbit something like this, a limit cycle, then in order to study its stability, what we will do is we will obtain a Poincare section and it will be seen as just one point. So, on the Poincare section it will be defined as a map x n plus 1 is equal to function of x n, and this specific point has the property that x n plus 1 is equal to x n, this particular point, and there is a fixed point. Then our ultimate question was how to study the stability of this orbit. Now, it is not difficult to see that if the orbit is stable, then if you start from an initial condition away from it, then in successive rotations or iterations on this Poincare plane, it will come closer and closer to that specific fixed point. So, you will see a sequence of points, a point mapping to a point, mapping to a point, mapping to a point, but they are coming progressively closer to each other. Ultimately, it will converge onto that fixed point. So, whether or not this is true, we are trying to test. Now, if you have an equation something like this, normally this function will be a nonlinear function, some nonlinear function. In that case, if I say that here is my fixed point and I want to study the local linear property, what will I do? Suppose this is a two-dimensional system as I have depicted there. In that case, it will be x n plus 1 is equal to some function f 1 of x n and y n, and y n plus 1 is another function of x n y n. Here these are the vectors. Now, I have written in individual scalar terms. In that case, your local linear behavior will be something like this: x n plus 1 y n plus 1 is something times x n y n. Now, what is that something? It is again the Jacobian matrix, which is fine. Having obtained that, we would have numbers here, because whatever will appear in these parts are functions, and then if you substitute the position of the fixed point, you get numbers here, and those numbers again in the matrix will yield eigenvalues. Now, what would those eigenvalues mean? What they would mean is, for example, here I am drawing a discrete state space. So, this is discrete, remember, which means points jump from one point to the other or map from one point to the other, and say this is the point, this is the fixed point. So, if this matrix yields real eigenvalues, then there would be real eigenvectors also. These will yield. So, this is x n plus 1 is equal to A, so that matrix times x n. These are vectors. These are x n plus 1 and x n are vectors. In that case, what would the implication of the eigenvalues be? Notice again we would say that in this space there would be two directions such that if you take an initial condition on one of these directions, eigen directions, then in subsequent iterations it will remain on that. That is the definition of the eigenvector. So, you are taking an initial condition x n on that eigenvector. In that case, your x n plus 1 will be the eigenvalue times that. Okay. See, what does it do? A matrix operated on a vector is giving a vector. Earlier, when we were dealing with equations of this form, x dot is equal to f x continuous time dynamical system, then also this was true, x dot is equal to a x, and then a matrix operating on a vector was giving a vector, but this vector was the velocity vector x dot. In this case, what does it give? A operated on x gives what? Not the velocity vector, but exactly where it lands in the next iteration. So, that is one essential difference between a continuous time dynamical system given by this and a discrete time dynamical system given by that. So, A operated on x, x is the vector, gives the vector where it lands, actually lands, not how it moves. So, if the initial condition is here, say in the next iterate it jumps like this. Then this distance divided by that distance will be the eigenvalue. So, or this is the initial distance. So, what will you say? If you have this in the eigen direction, then x n plus 1 is equal to lambda x n. Lambda is a number. If that number is say 0.6 or so, then what will happen? If you have x n here, times 0.6 will be x n plus 1. So, this is x n plus 1 and this is x n. Is that right? So, you know already how to obtain the eigenvalues of a matrix. So, I am not repeating all that. This is rather trivial, but here you have a conceptually slightly different situation where the scalar number lambda operated on the vector is giving me the next iteration here. So, when will I say that this fixed point is stable? When the next iterate lands closer to it. Okay. And if you operate again A on x n plus 1, you will get x n plus 2, which will be further closer, and in further iterations it moves closer and closer to the fixed point and ultimately converges onto it. So, what is the condition for that to happen? Now, notice the lambda is simply multiplied with the initial vector to give me the final vector. What should the condition on the lambda be so that it lands closer? It should be less than 1. Okay. Notice here an important difference with continuous time dynamical system. We had decided that the condition for stability is that the eigenvalue should be negative for continuous time dynamical system. Here the eigenvalue should be less than 1. Clear? What happens if it is negative? Yeah, it goes to the other side. Say if this is a fixed point and here is the initial condition and the eigenvalue is negative, what happens? This initial vector multiplied by a negative number will come somewhere here. In the next iteration it will come somewhere there, and so on and so forth. It will toggle, it will flip between the two sides and ultimately it will converge onto that, right. So, still here the condition is what? The magnitude should be less than 1, that is it. So, I do not care whether it is negative or positive, the condition really is that the magnitude of that of the eigenvalue should be less than 1. Clear? So, now notice the whole thing that we have done. We have started with a continuous time orbit like this. We have observed it in each piercing. As a result, we have obtained this map. If we have obtained this map, then we would simply locally linearize around this point by obtaining the Jacobian. This is the Jacobian matrix. Where is it? If you have obtained this, then we will write down the Jacobian matrix. We will obtain the eigenvalues of it, and if the eigenvalues are less than 1 in magnitude, we would conclude that the system will be stable. Which system? This orbit. So, we had initially landed with a problem that in nonlinear systems we have not only equilibrium points, but also periodic orbits like this, and those orbits are also important in nature as well as in engineering. So, we are interested in their stability. So, we decided that instead of, we cannot handle that stability, or we cannot probe the stability simply by locally linearizing in the continuous time space, state space. Why? Because it is not a fixed point, it is not equilibrium point. None of these points on this orbit are equilibrium points, we cannot do that. So, we took a Poincare section, then on that we obtain the map. So, what is the character of the fixed point? The fixed point is exactly representation of the periodic orbit, right, because it falls exactly there. So, the fixed point is exactly the periodic orbit. Then in order to study the stability, all we need to do is to obtain the Jacobian and find out its magnitude of the eigenvalues.
Sir, I have a doubt. In the finding the Jacobian, you are differentiating the discrete function with a discrete variable.
Right.
But if the function is discrete,
Okay. His question is that in obtaining this, we are differentiating a discrete function with respect to a discrete variable. How is it possible? Okay, I will deal with that question. Okay, in order to deal with that question, let us try to understand it in one dimension. Why? Because in one dimension there are a few advantages. Let me clarify that. In one dimension, the equivalent of the Jacobian matrix is nothing but the derivative. So, whether or not we can take the derivative, that is what you have to understand. Okay. In that case, we have to take a larger system, a system where say there is an orbit something like this in 2D space. Then how can you place a Poincare section? Then just a line will be the Poincare section. Just a line will be the Poincare section. If this is your limit cycle, in that, then this will be it will go like this, and you can say that okay, this line is my Poincare section. So that this point maps to this point, maps to this point, and so on and so forth. Clear? Now, if we start from that premise, then it will be somewhat easy to proceed, because then we can possibly do the whole job with just one dimension, right. Let us start with a problem where you have this kind of a orbit in 2D. Consider the set of differential equations r dot is equal to b r 1 minus r and theta dot is equal to 1. Okay. Start with this set of differential equations. So, theta and r immediately talk about the radius vector and the angle. So, it says that theta dot is equal to 1 means there is a radius vector which is turning, and theta dot is the same, which means is turning at uniform speed, right. And r dot, this radius vector, is changing, and the rate of change in this direction is given by this. Clear? If you put r dot is 0, then under what condition is that possible? R is 0 and r is 1. Okay. R is 0 means right here. So, there is an equilibrium point right here, but there is also something very important at r is equal to 1. What is it? If r is 1, that means this radius vector is 1, then r dot is 0, which means it does not expand or contract. Okay. Moreover, if r is between 0 and 1, then what is the r dot? Between 0 and 1, this is positive number, this is positive number, therefore, r dot is positive, which means it should be going out, r dot is positive. If r is greater than 1, then what? Negative, which means it will come back, which immediately means that it harbors a limit cycle at r is equal to 0. Right. Start from an initial condition inside, it will go outwards and converge onto it, and start from an initial condition outside, it will again come inward from outside and will converge onto it. Okay. So, we have got a typical example of a dynamical system. Okay, it is a toy dynamical system, all right, but nevertheless it has the property that we wanted to study, and it turns at a constant rate of theta dot is equal to 1 radian per second. Now, how do we then discretize this system? We have to place a Poincare section, and that Poincare section could be placed just anywhere. There is no distinction between this point, so it could be placed at any arbitrary angle, say this angle, let it be theta dot, theta naught. Okay. So, in that case, what we will ask? On this Poincare section, if we start from an initial condition somewhere here, where does it land next? Okay, if I start from initial condition somewhere here, where does it land next? Clear? So, we will essentially be talking about an orbit like this. It started from here and it landed here. We have already decided that the r dot is negative if it is outside. So, it is landed here. So, what are you trying to find out? We are trying to find out this r initial is mapping to the r final. So, this point is r n, nth point say, and this point is r n plus 1. So, our objective now is to find out r n plus 1 in terms of r n. That will do, fine. Now, to your question, it is not really, though we are talking about discrete jumps, but actually you could frame this question. Suppose I now move r n by a slightly different amount. Yes, it will come back to some other point, again slightly different amount. So, the r n is really a continuous thing, and r n plus 1 is also a continuous thing. Start from any place, we after having constructed the map, we should be able to answer the question starting from any point, where does it land next? Okay. Let's go about doing it, then it will be clearer. So, how do we obtain r n plus 1 in terms of r n? Since these two equations are not coupled, they are separate, theta does not appear in the first equation, we can solve the problem simply by integrating this. So, that is what we will do. So, we have here dr dt is equal to br 1 minus r. let us separate the variables. So, you have dr by br 1 minus r is equal to dt. Now, let us integrate it. So, can I move to the next page, but we will have to come back to this picture. So, just keep this picture in mind and let us do the algebra in the next page, because it may be little bigger. So, we had this equation, and then this will have to be integrated from Rn to Rn plus 1, and how much is the t is actually a complete rotation. A complete rotation is twice pi. So, the limits of the integration would be, this is Rn to Rn plus 1, what are we integrating? Dr divided by Br 1 minus r is equal to, t is integrated over some t naught initially, some time here, to t naught plus twice pi dt. Okay. Now, do this integration. You know how to do the integration better than me. B is can be taken out, be common. So, you have integral to Rn to Rn plus 1. We need to separate them out. It would be 1 by r minus 1 by 1 minus r, this whole thing dr, okay, is equal to, we can directly integrate it, it will be 2 pi. Which one? Plus, right. So, then we can do the integration. Let us take the b to this side. It will be ln r plus ln r minus ln 1 minus r. This will be from Rn to Rn plus 1. Okay. B has come to this side, so twice b pi. Okay. Then this will be ln of, I want to write Rn plus 1 in one side and Rn in the other side. So, it will be Rn plus 1 by, just check the steps, 1 minus Rn plus 1, this is one term, and the other term is 1 minus Rn by Rn is equal to twice b pi. Fine. So, now we can, since we have taken the ln out, we can get this out, and this would become exponential twice b pi. Then we can extract it out. So, it will be Rn plus 1 divided by 1 minus Rn plus 1 times 1 minus Rn by Rn is equal to e to the power twice b pi. Okay. So, from here we can easily extract Rn plus 1 in terms of Rn, just algebra from here. So, if you obtain it, you will get Rn plus 1 is equal to Rn e to the power twice b pi divided by 1 plus Rn e to the power twice b pi minus 1. Fine. Now, notice his question, Rn could be just anything. Rn is at the nth iteration, if the distance is this much, where will it land next? That is the question we are asking. So, this much is, it could be anything. We could ask this question related to anything. There is no reason to say that it is 1 inch and not 1.1 inch. So, if this question can be answered with respect to 1 inch distance, it could also be answered with respect to 2 inch distance. It could also be answered with respect to 1.005 inch distance, and therefore, Rn is a continuous variable. Rn plus 1 is also a continuous variable. Okay. So, even though we are talking about discrete jumps, ultimately we have obtained a function and it is a continuous function. Clear?
In the limits of that integration, during when we are integrating the time, we put that from t0 to t0 plus 2 pi. I said 2 pi is angle and t0 is time. So should it be?
No, the time scale is just 1 radian per second. That is why. See theta dot. No, that is why we did that. This is a special case. That is why. Normally, you would have to take that into account. Okay, now, so is that clear? In general, therefore, we will get, for a 2-dimensional thing, we will get a 1-dimensional map like this. So, if it is a 1-dimensional map, the advantage is that we can draw a graph of the map. What does it mean? It means that we can draw, say, we have obtained x n plus 1 is equal to some function of x n. This is 1D, so I am not writing it as vector. So, here I will write x n and here I will write x n plus 1. This function can be plotted as a graph. This cannot be possible in 2 dimension or higher dimensions, but in 1 dimension it is possible. For example, this particular function, what will be the character? If Rn is 0, then what is Rn plus 1? 0. If Rn, okay, can we now differentiate Rn plus 1 with respect to Rn? We can. At Rn equal to 0, what is the slope? If you do it that way, you will find that it has a shape something like this. So, you draw a graph. It is possible to draw a graph, and then you will see that much can be obtained simply by looking at the graph. Much can be inferred simply by looking at the graph. Like what? Like, for example, if I ask you, what is the fixed point of this system? It can be simply obtained by drawing the 45-degree line and here it intersects. Where it intersects, x n is equal to x n plus 1. So, that is the point which is the fixed point. So, the fixed point is obtained simply as the intersection of the graph of the map with the 45-degree line. Okay. The equivalent of your Jacobian matrix is nothing but the slope, the derivative. Yes, you can take a derivative now. You can see at every point you can take a derivative. Fine. And what is the meaning of locally linearizing at the fixed point? It is just this line having a specific slope, a straight line which is tangent to the graph of the map at the fixed point. Fine. Now, then much more can be inferred if we look at this graph, because if the initial condition is close to that fixed point, then it will more or less follow this particular straight line. So, let us try to understand what happens if you have this straight line. Okay, before that, let us try to understand something more. When we have x n plus 1 is a function of x n, what actually is x n is a point on the real line, any point on the real line. What does f x n do? It takes it to another point on the real line. It is like, suppose this is a real line and here is my x n, and then this function is saying that in the next iteration it will jump there, in the next iteration it will jump here, in the next iteration it will jump there, so on and so forth. That is what it is saying. Now, that can also be obtained graphically. How? Suppose your graph of the map is as we have drawn for that example system, like this, x n and x n plus 1, and this is the 45-degree line, and here is our fixed point. Then suppose we have started from initial condition somewhere here. Okay. What will be the next value of x n plus 1? It is just this. If you go up, it is this value. Okay. If you now want to iterate, what will you do? X n plus 1 we will have to give rise to x n plus 2, which means this value you will have to take along the x axis and then find out where it goes next. Okay. A simple way of doing it is to come to the 45-degree line and come down here. So, this is your x n plus 1, right. So, here we went up to the graph of the map and then we wanted to bring this one here, that is what we have done. Okay. This part we have brought here, and what will be x n plus 2? Simply from here go up to the graph of the map here. So, this is x n plus 2. Where will be x n plus 3? Simply come to this, and here this will be x n plus 2, and then go up to the graph. This will be if you go to the 45-degree line, you come down here, this will be x n plus 3. Here is your x n. So, what has happened? On the real line, we started with x n, it jumped to x n plus 1, it jumped to x n plus 2, it jumped to x n plus 3, and so on and so forth. Do you see that it is, the distance is progressively going down and it is converging to something, right? Converging to what? The fixed point. Why? Why and under what condition would that happen? Let us try to consider that. Fine. Now, in order to consider that, this is the 45-degree line, and let us say the graph of the map is like this. I am taking only the tangent to it, so that we are essentially blowing up what happens in this neighborhood. Now, suppose you start from this point, I will draw in red. Start from this point, how will you go? This is my x naught, say, starting point. Then I will go up this way, go this way, go this way. Then you see that it is converging, it is progressively converging. Why did that happen? That happened because what should I say? Because the slope of this line is less than unity, therefore, this line is always bigger than this line. So, it will always go like this and converge. Just contrast it to the other case. Suppose you have I'll draw in another page. And suppose the graph of the map is like this, with the slope bigger than 1, and suppose you start from an initial condition, say here, okay, say I'll start close to the fixed point. You will go like this. Next iterate will be here. To obtain the next iterate, you will have to go to the 45-degree line. Again, come down here. Again, come down here. It's going outwards. Start from a point very close to the other side. Going outwards. So, you can see that we are doing it completely graphically. We can easily do that by pressing a calculator, all right, but nevertheless we are trying to develop an understanding, graphical understanding, and we can see that the moment the slope of the graph is greater than 1, it goes further iterations go outwards, go away from it, and so the system is unstable. While in this case, if the slope is less than 1, it is stable. That is what we have decided really. When we talked about the eigenvalues, we decided that the slope, in that case we talked about the eigenvalues becoming less than 1 will guarantee the stability. Here the eigenvalues are equivalent to the slope, and the slope becoming less than 1 will guarantee stability. Okay. The slope where? The slope at this point. Okay. Slope where? The slope at this point. So, again let us take stock of the situation. We said that a continuous time orbit, we had difficulty in studying the stability. We said that we will place a Poincare section, obtain the map, then obtain the local linearization by taking the Jacobian. If it is a 1D map, the Jacobian is equivalent to taking the derivative. Fixed point is obtainable by the intersection with the 45-degree line, fine, and then the stability of that whole system is given by the slope at that particular point. Is that clear? So, we have essentially solved the problem of stability of the continuous time orbit, that was a limit cycle. We understood how to tackle the question of stability of the limit cycle. But now there is something more to it than meets the eye at this stage. The point is that in a linear system, if you find that by obtaining the eigenvalues around an equilibrium point, you find that the eigenvalues have positive real part, you know that it will become unstable. Unstable means initial conditions, starting from any initial condition, it will run to infinity. The system is unstable, system will collapse. One peculiarity of a nonlinear system is that even if a system can become locally unstable, there is no reason to believe that it will globally unstable. So, if one behavior becomes unstable, another behavior can become stable. Let us illustrate that. Suppose we take a map x n plus 1 is equal to a minus x n square, a very simple nonlinearity, just a square. How will the graph of the map look? Parabola, right, parabola like this. So, say this is the parabola, how will it be? Yes, okay, it can to start from anywhere, right? Okay. So, where is the equilibrium point? Where is the fixed point? Here. And what is the slope of this? Notice we can do that by hand. We can do that by hand. How? What is the slope of this? dxn plus 1 dxn is equal to minus twice xn. What is the slope? In order to know the slope exactly, we have to substitute xn. That means we have to substitute the condition for the fixed point. What is the condition for the fixed point? xn plus 1 is equal to xn. So, the fixed point is given by xn, I will call it xn star, is equal to a minus xn star square. So, this gives a quadratic xn star square minus xn star no plus minus a is equal to 0. So, xn star is equal to minus 1 minus half plus minus half root over 1 minus plus 4a, right. So, it depends on the value of a. The position of the equilibrium point depends on the value of a. Now, suppose we take a certain value of a, then we will get this position exactly and substitute that here, we will get the slope exactly. Now, if I ask you at what value of a does it exactly become minus 1? Can you say? You can easily say, because in that case it will have to be half, and in order to get half here, what do you have for a? You can easily calculate. Got it? So, this is a parameter. At a specific value of the parameter, the slope becomes exactly minus 1, and we know that when it becomes minus 1, it will become unstable. Exactly what happens when it becomes minus 1? Let's check out. If you have the slope of the graph like this, exactly no, slightly less than minus 1, I am doing. Then how will the iterations go? Iterations will go like this. Then to the 45-degree line, to here, fine. So, if the slope is less than minus 1, then it will go like this. Have you understood this graphical iteration process? We are first going to the graph of the map, then the 45-degree line, again go to the graph of the map, 45-degree line, and so on and so forth. If the slope is greater than minus 1 like this, then how will it go? It will go like this. Will go out. So, the limiting condition is exactly minus 1. So long as it has a slope less than minus 1, then it will be stable. If it becomes a slope greater than minus 1, it will become unstable. Good. So, in this case, at a specific value of a, it becomes unstable. Below that, it will be stable. So long as this magnitude is less than minus 1, it will be stable, or after that it will become unstable. Clear? Now, when it becomes unstable, at this point the slope has become greater than minus 1. So, let me draw it separately. slope has become greater than minus 1. So, take any initial condition close to it, it will diverge out. But will it be able to diverge out indefinitely? No, because the slope is reducing here. So, after some time it will reach a state where it will become like this. It will be like this. What does it mean? It means that it has become what? A period 2 orbit, because it is toggling between two values. It is going from here to here, again back here. What is meaning in continuous time dynamical system? Because ultimately what are we doing? We are looking at the Poincare plane and what is happening there. There we find that it has become a toggling between 2 points. What is happening in the continuous time dynamical system? It is actually now an orbit like this. Sorry. A period 2 orbit. So that if you have there are two intersections. Fine. So, this is how, even though one fixed point becomes unstable, the system does not become globally unstable. It is only locally unstable, but globally another behavior develops, a period 2 behavior. So, similarly you can figure out that in a nonlinear system, if some part of the space becomes unstable, that does not mean it is globally unstable. You have a large number of possibilities. Then the whole state space will be divided into parts. In some parts, okay, it is unstable. That does not mean it is elsewhere unstable. In this part, if it is unstable, means a whole orbit can become stable. If this whole orbit becomes unstable, still a period 2 orbit may become stable. If period 2 orbit becomes unstable, still a period 4 orbit may become stable, which means that the stability needs to be understood in a different context in a nonlinear system. In a linear system, the stability is often understood as whatever we infer at a local level is also true at a global level, while in a nonlinear system, whatever is true at a local level is true at a local level only. You cannot extrapolate that idea to a global level. So, with that understanding, let me illustrate a few things on the computer before we stop today. For example, here is the map that I just not that. Here is the map called the logistic map, which is x n plus 1 is equal to a, or the normally it is written as r x n 1 minus x n. R is the parameter. So, in order to study this behavior, its behavior, what will you do? You will start from any initial condition and go on iterating it. So, start from x naught, this will give you x 1, put that back here, it will give you x 2, put that back here, it will give you x 3, and so on and so forth. You get a sequence of numbers. Now, if this were, say, do you see that all of them ultimately starting from some initial condition converge onto a number and then steady there, flat. Start from a smaller number, smaller value of the parameter say 0.8, it goes to 0. Start from any initial condition, you get a sequential number that goes to 0, everything dies down. But if you start from, say, the parameter r is equal to 2, then it goes to a definite value. Good, that is fine. But now make r 3. See, it toggles between two numbers. Yes, there is the initial transient that goes for a long time. Let me make it slightly bigger, it will be better. See, there was some initial transient but ultimately it converged onto two states repeating each other, which means it is a period 2 orbit, which means it is a period 2 orbit. In the continuous time dynamical system, it is a period 2 orbit like this, but here it is seen as the state toggling between two numbers. Good. Let me now increase the value. Oh, it's too heavier. It is still a period 2 orbit. I have now put 3.4, I will now put 3.5. It is a period 4 orbit. So, I am changing the parameter, it is going from dying down to 0 to period 1 orbit, period 2 orbit, period 4 orbit, and then if I further increase it, it is completely, what is it? Chaotic, because the state, no state is repeating itself. No state is repeating itself. Yes. So, no state is repeating itself. Are you happy? Now, let us take a look at it from the point of view of graphical analysis. So, let me start with, we started with 0.8. See, then this is the graph of the map, and since the slope here, this is the fixed point, since the slope here is less than 1, therefore, starting from any initial condition it goes to, how can you see how it goes? Fine, let us change it to 1.5. See, now this is a fixed point, this is another fixed point, here the slope is greater than 1 and here the slope is less than 1, and so starting from an initial condition it converges onto that. Fine. Okay, now let us make it 2.5. The slope has increased, but it goes like this and finally converges. But here at this point the slope is negative, so it converges from both the sides. Let us increase it 2.9 maybe. Can you see how it is converging? It is converging from there. Fine. Okay. Now, let us make it above 3. See, it goes there, and then after that it goes out, because this point has become unstable. As it has become unstable, it goes out, but after that this orbit, a period 2 orbit, has become stable. That is what you saw earlier, the same map, that is what you saw earlier when it was a toggling between two values. All that can be inferred graphically. Now, let us increase it to 3.5 or 3.4 we had to. Still period 2. Can you see now it is period 4. Let me do that again. 6. No, it is gone out. So, it is now going on with that. Let me increase it, then it will be clearer. See, now same points are repeating. It was homing onto that, that is why this part you find a little thicker, but actually it has homed onto a period 4 orbit. But now, if I increase it to a large value, it is completely chaotic, but now I will have to draw a large number of points, otherwise it will not be clear. Now, keep on seeing what is it doing. No point is repeating itself, right, and that is what is chaos. So, we can see that even with this very simple map, which you can do any algebra with simply by hand. Still you can find this kind of completely chaotic behavior appearing in it. Okay, that is enough for today. Let us call it a day.